All right, what was due today is chapter 10, homework number 3, questions 13 through 16. This is dealing with simple machines. The first one here talks about a sledgehammer drives a wedge into a piece of wood. The wedge is driven 0.2 meters into a log, and the log separates by 0.05. We all know that it would be very difficult to split a log with your fingers, right? To, grab into kind of a crevice that's there with the log and spread it apart is pretty much impossible. So we use a simple machine. So what happens is a wedge, which has a shape like this, when you push that down into the piece of wood. Sorry, I'm not an artist, so if this doesn't look very good, I think you understand at least the idea. It's actually not that bad. When you hammer with the sledgehammer downward, you're exerting a force, which is still pretty large because of the fact that you're swinging it, but it's nothing compared to the size of the force that the wedge then puts outward onto the wood. So this force right here, we'll call it F out, is equal to 19,000 newtons. Okay, so that's pretty incredible. Your swing with the sledgehammer, well, I was about to make a guess as to what it is. Why would I make a guess when we're about to solve for what it is? How far the wood separates is going to be a very, very small distance. We'll call that D out. And how far the wedge is driven downward, we'll call that D in, is going to be a much bigger amount. Now, this was kind of a confusing one compared to questions 14, 15, and 16, I think. On your tests, I'm planning on doing something with the levers or leverage, or possibly with a pulley system. Your job is just to look through the numbers that we're given here and try to see if you can figure out what they are. So for example, they give us a 0.2 meters. That's some kind of distance. They give us a 0.05 meters. That's some kind of distance. They give us a force. That's some kind of force, newtons. And then they ask about another force. Now, they specifically say, what is the input force, which is the question mark. All right, so then all of that information is supposed to get us to say, oh, we're dealing with simple machines. Fn times Dn equals F out times D out. Let's get the chat going here in case there's anything you guys have added. I saw it blinking a little while ago. No, nothing new. So there's what we have for our equation. All right, so now you've got to dissect this and try to put in the information into the correct places. So we're going to put in 19,000 in for F out, and obviously we're going to leave F in as our variable. And then now we have to decide what to do with the other two numbers there. Now the context of this problem says the wedge is driven into the log. So that is something that tells us that the wedge is where we're supposed to put in the 0.2 meters. And then the log, which is where the force is being applied to the log, is where we're going to put the output distance. Okay, so that would be one way how I know where to put my two distances. The other way that I know how to put those two distances is because what we said about these in the notes on Thursday is that in order to exert a smaller force, the smaller force has to be exerted over the bigger distance. And so I want the bigger distance on the side with the smaller force and the smaller distance on the side with the bigger force. If you still don't see that, you could try it with the two distance numbers flip-flopped and see what answers you get. Look at your answers and then don't just put your answer and walk on. Look at your answer and think about if it seems right or not. So when you put this in here, does it make sense that you would put in about 5,000 newtons of force to get 19,000 newtons of force out of it? That seems reasonable. If you do it backwards, you're going to end up with the answer coming out to be something around 100,000 newtons of force. Seriously, you're going to be able to apply 100,000 newtons of force with a sledgehammer? Doesn't seem very realistic. But this question is kind of difficult anyway, so therefore, if you got confused on number 13, do the best you can, but it's not the end of the world. Question number 14, we are making a pulley system. How many pulleys are in this pulley system doesn't really matter. So like the easiest way to draw it would be just to put two pulleys. Here's a mass that you're lifting, and then there's a string that goes something like this. Okay, and then as you pull down on this with your input force, what happens is it lifts the mass up with the output force. All right, the distance that the output force lifts is called d out, and the distance that you pull down on the string or the rope is called d in. All right, now if I put this on a test with pulleys, I'm going to have a picture on there. So I do want you to be able to, not just read the words, but also recognize, what is where. Ideal mechanical advantage and real mechanical advantage. You see that look on my face right now that says, I don't know which formula is which. Why would I memorize that when I have one of these? On this cheat sheet, it says that the ideal mechanical advantage formula is where we do a comparison of the distances. It specifically says that IMA is equal to D in compared to D out. All right, so then your input distance is what is exerted on the rope, and that is 33 newtons. I still think that this question is even written a little bit more difficultly than I would put on a test. On a test, I don't want it where you would have to read the words of this and try to see if you can decipher which is which. I'd rather you be able to look at a picture and be able to tell immediately which is the input distance and which is the output distance. So far, I'm not happy with my first two questions on this homework assignment. We divide those two numbers and get 2. I probably should have been able to see that without even looking at the answer. We get an answer of 2 for the ideal mechanical advantage, which actually that is what a 2-pulley system does give you, is a mechanical advantage of 2. Now, the real mechanical advantage is a comparison of the forces. This is where you compare the output force to the input force. Notice that the two formulas are flip-flopped of each other. How are you ever going to remember that? Because you're going to use this, right? It's always the big number divided by the small number. That's also something that can be used. 240 newtons divided by 129 newtons. That comes out to be 1.86. So ideally, a pulley system is supposed to give us a mechanical advantage of 2. In other words, it multiplies the force by 2. It makes it half as hard to lift something. But really, it's a little bit less than that because we have some friction with the pulleys, which means that you're going to have to put a little bit more force in than half as much in order to actually get it to lift up. So that's the 1.86. So then that allows us to do an efficiency comparison, which is where you can do a comparison of the mechanical advantages, 1.86 divided by 2, and then because it's a percentage, you times it by 100%. If you don't do that part and just leave it as 0.93, that's okay too. All right, so those are two kind of confusing questions. If those didn't settle well with you when you did your homework assignment, just let it go because I don't really like those for a test question as much as I like a question like number 16. 16 is a perfect test question. Before we get to that though, number 15 says, a boy exerts a force, that's going to be the input force, to raise a lever that is pushing on a rock. 1.25 times 10 to the third is really 1,250. Doesn't that make sense that leverage can allow you to exert a much smaller force to lift a much heavier object? The rock is raised a distance of 13 centimeters, so I'll put in 0.13 meters, and we want to know how far did the boy have to move the lever. So you're now solving this equation. That's a pretty straightforward problem. That one wasn't too bad, but I still like number 16 better because of the picture that accompanies it. I don't know that I'm going to label everything with D in, D out, F in, F out. I'll probably just label it as D's and F's and then have you know what numbers go where. We'll see. By review day, I'll be able to give you a better answer as to how this is going to look. Solve for D in. Multiply, then divide by 225. My calculator says that the boy has to move the lever 72 centimeters. That's a big distance. 72 centimeters is, we're talking about maybe 3 feet. So what's the, a little under 3 feet? What's the trade-off there is you move the rock that you otherwise would not be able to move. So that's what leverage does. Last question, number 16 says, a lab group makes a lever out of a meter stick. The fulcrum is at the 30 centimeter mark. That's right here. The object is at the 10 centimeter mark. That's right here. That tells us then that our output distance is from the fulcrum to where the object is located is 20 centimeters or 0.2 meters. All right, that's pretty straightforward. The scale that is lifting this object reads 2.5 newtons. That's what our Fn is. I like this question the way this is actually, with all the numbers on here and everything labeled. This is a really easy one for me to make a test question out of, because what I'll do is just shift where the objects and where everything's at, what the scale reading is, or I'll tell you what the mass is and ask you to tell me what the scale reading is. One form of the test, maybe I'll give you the two forces and ask you to tell me what the distance is out to the scale or to where the object is. So just one of these four things is going to be your variable in this equation. So any one of these is fair game. You guys can handle that. The scale reads 2.5 newtons and is located at the 90 centimeter mark. So if it's at this location, the distance from 90 to 30 is 60 centimeters or 0.6 meters. That's not going in the right place though. That goes right here, 0.6 meters. We want to know what is the weight of the object. And so we plug in and solve that. I should have put more of these questions on your test. Be ready for number 16 for your, I'm sorry, on your homework. Be ready for number 16 for your test. You had maybe 2 or 3 of these in your notes, plus you have this one, and there should also be some in the review. They're pretty straightforward. They're not that hard. We don't need to practice that many of them, but be ready to be able to do those. 7.5, apparently. Any questions on your homework before we start today's notes? All right. Today's notes are, I think, pretty easy. We're just looking at 2 of the common forms of mechanical energy. We already talked about these back at the very start of chapter 10, so that makes this even easier. So we'll start with kinetic energy. We have an 875 kilogram car that's going to speed up from 22 to 44 meters per second. How much did its kinetic energy change by? So what are the initial and final kinetic energies? And then we can talk about that in terms of work. I'll give you a moment to copy that down. So the first part of this says, what are the initial and final kinetic energies? So I'm going to go with KEI and KEF. The formula for kinetic energy, we've already seen this before, is 1/2 mv squared. Since they're talking about the initial kinetic energy, I'll talk about the initial velocity. When they talk about the final kinetic energy, I'll talk about the final velocity. Then we put our values in here, our numbers. 1/2 of 875 times initial, 22 meters per second. And then for the other one, 1/2 of 875 times 44 meters per second. Notice that the velocity is squared, which means that if we double the velocity, we actually quadruple the amount of kinetic energy. I got 211, 750, and I got 847. And you should notice that those two numbers, the 847 is 4 times bigger than 211. Now, the next part says how much work was done. So we've learned a few things about work. One of the things we learned about work is force times distance. But the problem with work equals force times distance is we don't know how much force was exerted here. Some might say, well, could we use a motion equation to find the acceleration? The problem with that, you can, but the problem with that is the derivations required to get to a motion equation that shows acceleration is difficult because we need one more motion variable. Now, there is some substitution that will make that work, but it's really, really hard. So this equation, which is our default fallback for work, doesn't work in this problem. What does work in this problem is something that we said at the beginning of chapter 10, which is that work equals a change in kinetic energy also. If you do work on an object, you're going to change its motion. You're going to make it speed up or slow down, or you're going to make it go up or go down. So you can change its kinetic energy or you can change its potential energy. If I give this to you on a test question, it will only be in this format, be just like example 1. So now all we do is just subtract the 847 minus the 211. Change in kinetic energy. If you'd like to see that written out in your notes, we would say that that's equal to KE final minus KE initial is what I did there. See it on that slide pretty well too. All right. Hey, example 2, and we are also all done once we finish example 2. Potential energy, there's many different forms of potential energy, but the most common one, especially in a physics class, is gravitational potential energy. But we could also talk about like food potential energy, right? We have energy that's stored inside the food as calories that you could use to create movement. We could talk about chemical potential, that's really chemical potential energy. We could talk about chemical potential energy inside gasoline, ready to burn, combustion in a car engine and make the car do work, make it move forward. So there's many different types of potential energy. In fact, there's even one at the bottom of this slide that you might need. I don't know that you need it tonight's homework, maybe, but you definitely will need it in a section coming up. 11.4 deals with potential energy stored in a spring. So these are all good forms of potential energy, but the most common one is gravitational potential energy. And we've already seen this before. Its formula is mgh. So we need to know, what does something weigh? How high above the Earth's surface is it? And by the way, in order to give an object potential energy, normally something has to do work on it. You can read that into example 2. It says, somebody, you, lift a 2-kilogram book from the floor to a shelf 2.1 meters above the floor. What is the potential energy relative to the floor? So to find the potential energy relative to the floor, I've had this example in my notes since my first year at Granite Hills High School in 2000, or 2001 maybe is when we actually covered this, somewhere in there. And I've always thought, what a lame example. I don't know why I haven't changed it to be something a little bit more exciting. You lift the book up, onto a shelf? That just doesn't seem very exciting, but it is what it is. 2 kilograms, you could have just called that 2 kilograms times 10 and call it 20 newtons. But if we were to write it out the way the formula is written there, it's really 2 kilograms times 9.8. That right there is force. And then how high up it's lifted to, 2.1 meters, is distance. So I don't know if you want to write this down. I'll leave it up to you. I'll put it in red, so it's your choice. Here is your force. Here is your distance. And we know that force times distance equals work, which means that if you do work on an object, you could either speed it up or slow it down, or you could raise it up or lower it. So you could change the potential energy or you could change the kinetic energy on that object. But we don't need to make that connection here in this one, because if it's just simply asking for the potential energy, use the formula and multiply all those numbers, comes out to be 41 joules. If you drop that book in the notes tomorrow, we're going to see how fast that book is going right before it lands on your big toe. It's going to hurt, right? But if that book drops and only hits you on top of the head, it may hurt, but it's not going to hurt as bad as it would to your big toe because it's not going as fast. Why is it not going as fast? Because the amount of potential energy it has with respect to where your head is a lot less, right? We would say that with respect to your head, it's still a 2 kilogram book. It's still 9.8 meters per second squared of gravity. But now instead of putting in 2.1, I'm not even going to put in 1.65. Maybe I should have drawn a picture for this problem. So here's our shelf. We've just put a book there, and maybe the shelf starts to bend over a little bit such that the book slides off of the shelf. When it hits you in the head, it's not falling very far. So if this distance is 2.1 meters and this person is of a height of 1.65 meters, the difference in heights here, now I kind of ran myself out of space, is 2.1 minus 1.65 is our height difference to find out the potential energy relative to the head. I'm going to write that in right here though, 2.1 minus 1.65. And then do the math. Here's the difference right there. So potential energy is always relative to where you're at. In AP Physics, there's a question about Spider-Man, and Spider-Man has scaled like a tower on top of a building. Wouldn't it make sense that if Spider-Man is on this side of the tower and falls and lands on top of the building, might survive it? It's Spider-Man, right? If Spider-Man falls off this side of the tower, you better be able to use that little web thing to turn it into a pendulum so that it doesn't hit the ground. So we recognize that the difference in heights is a difference in potential energies, means a difference in how hard you slam into the ground. So I think that's the point of example 2. It's just not very exciting. Okay, that's really all I've got to talk about today. It's just a repeat of what we did at the beginning of chapter 10.1, looking at kinetic and potential energy. So here's what your assignment looks like. You've got 6 questions. It looks like there's a lot of words there, but these are just quick one-line answers for each of the parts. So please do your homework. Be conscientious about it. All right, I'm going to stop the recording.